Thanks for coming on the last day of TechEd. My name is Marco Manuello. This is my first session here, so you probably haven't heard from me except if you were at TechEd many, many years ago. The session is called Scale Up and Scale Out on Microsoft SQL Server, but before I start with this, there's actually one thing that I would like you to do, not immediately, but when you leave the session, which is our nice evaluation forms, and you've probably heard this by every single session, you're tired of it, but you have absolutely no idea how seriously we take those. So if you mark sessions bad, there's a good chance they won't be there next year, and you'll derive the benefit of not listening to it again. If they're really good, we really, really look at this. You should see what happens in the speaker room. The only thing they do is look at the stats on how the session got evaluated and what the comments actually were. So you do us a great deal of favor, and actually you get the results next year by hopefully getting an even better TechEd. With that, back to myself. As you can see by the name and maybe hear by the accent, the name is Italian. I'm half German. I used to work for Microsoft in the US for a long time, over 10 years by now. Moved to London, now work for Europe, Middle East, and Africa. And I'm in an organization that is called CADM. And you can always tell that we are a big organization because if I tell you what CADM stands for, you'll say, oh my God, it's Customer Advocacy Technology Management. And if you think about it, it doesn't really mean anything. What it actually means is that I'm one of the guys that sits between the development groups, the product groups, business groups in Redmond, and the customers, most of them like you. So we go to customers, large customer sites. We talk in pre-sales environments mostly. We're not in support. We're mostly in pre-sales. And we take the feedback of very interesting deals or of very interesting workloads, very interesting ideas that customers have. Not always negative feedback, but just looking at what is going on in the marketplace. And we bring that back to Redmond saying, you guys in Seattle, this is what we really hear in that region. There are some very interesting customers, and it's not necessarily driven by quantity, it's actually really driven by quality. So you don't have to be Siemens, Nestle, or BP. It could be a very, very specialized, small little company, but if they have a very good idea, or if they have something that we actually say, why didn't we think of this before, we take that feedback back. Obviously, the flip side of this job is that I a lot of times have to explain that some things are features and not bugs, because a lot of times the product groups come back to me and say, well, this is the reason we haven't done it. So this is my part in this. Which leads me to, if you have any suggestions, if you have anything like it, if you have any ideas, I take those very seriously as well. Please come after the session to me, and I'm happy to either give you feedback on that, if it has done before, or at least take notes and give you my contact info. With this, SQL Server scale up or scale out. So there's going to be a number of things in this session. It's going to be scale out, which is probably one of the reasons that a lot of people are here. And I don't know how competitive you are, if you're all really, really good Microsoft customers and you're paying a lot of our salaries, or if you're usually more mixed. If I could just get a quick hands on who is running SQL Server in a parallel distributed way, who is running, hands up, anyone? Okay, that's a good number. Anyone interested in doing it that is not doing it yet? All right, last question, anybody running competitors' products? All right, is anyone running Oracle RAC? Good, all right, yep. It's very interesting. I do those every once in a while, and there's definitely a good incline to see in there. I'll start with expectation settings right now. I'm not going to introduce a parallel distributed read-write database for SQL Server 2008. It's not going to happen, but you probably already knew that. So what I'm going to talk about rather is there's two parts, the scale-up approach. How do I scale up? What is really involved in it? And we're getting a little bit hardware-centric in this. Hardware-centric in terms of what actually makes a big difference for SQL Server when you're going the scale-up approach. And there's a lot of misconceptions in there. It's not going to be the easy one on like, well, just add another processor. It's really, I'll give you the percentage numbers in terms of what we find in very high benchmarks and in real-life loads, not just TPCC benchmarks. I'm actually not even going to go in there. What actually makes a difference, DDR2 RAM versus DDR3 and so on, because that ultimately inflicts everything else. There's going to be some interesting stories to that. And then we go into the scale out, where I'm going to go into distributed partition views. I'm going to go into peer-to-peer replication, have some demos on that as well. Most of this, what I have, is SQL 2005 based. 2008 is, in most of those things, not super different. We have a lot of performance improvements that I'll go into. But from a general architecture point of view, it's relatively comparable. With that, this is it. There's one last thing that I forgot to mention. Build a balanced system. I'll go into the definition of what a balanced system really is, and that is obviously not a definition that is in any official Oxford dictionary, but this is the way that we understand it. When I say we, I mean the guys, the SQL Server guys in Redmond that are doing a lot of the performance optimizations for partners and customers. So the agenda is very simple. I'm not going to spend too much time on it. Balanced system design, the scale up versus scale out. Just to ramp up to get a general understanding of what is going to go on. The scale up approach and the scale out solutions. The biggest problem we have that every database vendor in the relational or in the data warehousing space is addressing right now is, how do I scale in the best cost-effective way? So how do I get my first 10,000 users? And then after the 10,000 users, the second 10,000 users, how do I scale those second 10,000 users to go as fast as the first ones that I put on the box? And how do I do this very, very cheaply? There's two different ways of doing it. If you go down to the exhibition hall, it's more like 2.5 ways of doing it, depending on which hardware vendor you speak to. One is you just do the forklift upgrade. You take the box out, put a new one in, which is obviously bigger. And the second one is you just try to distribute your workload. In Germany, we have a saying that goes, everybody cooks with water, meaning there's no silver bullet. And it doesn't matter if you go to IBM, if you go to Adabas, MySQL, Microsoft, or Oracle. All our different designs have good parts and bad parts. And there's actually very, very good reason that we haven't gone what one of our largest competitors, run by Larry Ellison, is doing. And we're thinking about it very hardly, but we're not going to do the implementation like they have done, if we do it. So there's the scale-out approach to this. If we look at the pros and the cons, it's pretty straightforward. The scale-up approach, lower development costs in terms of, I don't have to architect my application to be multi-node aware. I don't have to do anything in order to spread out the workload. Easier to system administer it because it's one thing, it's one database, one server usually, that's it. And the trouble is, really, really expensive hardware. We go into this. What actually makes the difference? There's a lot of misconceptions in the marketplace. Versus the scale-out approach, which can scale extremely large. We have even customers that are doing our distributed partition views and other things over a very, very large number of boxes. And higher development costs. A lot of times you actually have to do some development on the back end to really be aware of it. So what is a balanced system design? A system where the most expensive resource can be leveraged to its maximum without any components of the system using the bottleneck. So I'm looking at it as, if I just look at the general box, it doesn't matter if it is scale out or scale up. If I look at any box, the optimum load is I can drive the most expensive part in that box without having another part of this box causing it to not do its load. Pretty straightforward, pretty simple. When we look at a server, we have several things on SQL: network cards, memory, processors, disk subsystem, file layout. And to go straight to the point, the most expensive resource in today's system by part is still the processor. It's not just the most expensive part in terms of money, but it's actually the most expensive part in terms of complexity in changing it. We now have boards that can easily add hot processor support. We have hot memory support if you go to our new operating systems. We can do all this, but nevertheless, there's always a certain limit. You can go to 64 gigabytes on the system. You can't easily on commodity hardware go to 64 sockets. So if we look at the balanced system, and we look at the different designs that are currently out there that allow us to do scale up and sometimes scale out, there's going to be three parts that we look at in the Microsoft world. The x86, that used to be the standard, and quite frankly, I'm not going to spend any time in this session to talk about x86. It's pretty much dead. If you have a high-end server, you don't want to see this, at least not anymore. We had the 4 GB memory limitation on 32-bit, 3 GB if you use the switch. We had AWE, the address windowing expansions, where we allowed SQL Server to use up to 64 GB using basically in-memory windowing, not paging, but we could only do data pages. We couldn't do block pages. We couldn't do anything, buffer pages, nothing but data buffer pages. It actually goes so far that when we release SQL 2008, we will have a 32-bit port, obviously, but our partners, to a great part, won't support it in enterprise-class servers. So SAP is a good example. When we shipped 2008, SQL Server 2008, and you're running SAP and you're planning on deploying 2008 on your SAP system in a 32-bit environment, it's not going to be supported by SAP. We need to get those servers out. The next one is Itanium. Everybody heard it. Everybody knows about it. Some newspapers actually call it the Itanic. It's not quite that bad. It's actually very, very good. But all of a sudden, we look at the market segment, and I actually, not too long ago, about a week ago, I got a question from a very good customer of ours, being rather concerned about the Itanium product line that we have, saying, well, Itanium came out, 64-bit came, and you guys are supporting it with Windows and SQL Server. And that's pretty much it. What is going to happen with it? Are we going to stop it? Is it going to go the way of the DAC Alpha or the RISC processors we supported and all those things that we had in the past, actually, if you remember back Windows NT 4.0? The good news is no, we don't. The reason that you don't see them is that the Itanium processors really are in a different reference design for us, and we are very, very committed to it because the biggest customers we have are almost exclusively all running on Itanium systems. And the trouble we have with the general perception in the marketplace is we always serve the 95% of the market capacity and the top 5%, the really, really, really high-end systems. This is where we see Itanium. Itanium just doesn't have the price benefit right now that would allow it to go lower. And at the same time, as long as it's a chicken and the egg problem, if we don't see enough customers to do and port more products to it, because it's a different code design, it requires different compilers, we won't do more products. It's very, very simple. We will always do SQL, we will always do Windows, and it will always be very, very well supported. But don't expect to get a native 64-bit Itanium Office 2007 or SharePoint 2007 for that matter, until we have a real need in the marketplace for that. Which brings us straight to x64. That was kind of a leading design by AMD. Intel calls it EM64T, which is the standard by now in any system. We can go to a lot more memory with this. We can linearly address it. SQL Server takes advantage of it, and guess what? It's fully 32-bit compatible, unlike Itanium, which does Windows on Windows. And it is somewhat compatible, but not 100% by software emulation. So the x64 is really this architecture that I'm going to talk about most today in this talk. So the biggest parts we have on scaling up is two different designs, SMP, symmetric multiprocessing, versus NUMA. And the standard boxes that most of us have are SMP designs. SMP usually has a limitation up around 4 processors. They're standard, nice, high-end servers. NUMA addresses a slightly different problem, and if you look at very, very high-end systems, we usually talk NUMA. What does NUMA stand for? NUMA stands for non-uniform memory access. And it's basically restricted, to the most part, to what we call non-commodity servers. Non-commodity servers are HP Superdomes, Genesis ES7000 machines, any of those. They use all the NUMA architecture design. The reason for all this is that it's very hard. You have a lot of concurrency issues if you would scale up with SMP more than that. The principal problem we had when we started with NUMA way back was there was actually a NUMA machine on SQL around 2000. That was Sequent, and a colleague and we worked on this in Redmond. It had 32 processors, 1632. The performance on this for SQL on SQL 2000 was less than a 4-way at that time. It was absolutely horrendous, and the problem was that we A, we were new to the concept of NUMA really, and B, SQL Server or Windows for that matter didn't really know that it was NUMA to begin with. The problem with NUMA is, if we look at the two different designs, on the symmetric multiprocessor you have a number of CPUs, usually no more than 4, connected to one memory controller, connected to the memory. So this CPU has the same latency going to that memory as this CPU has. There's no change. NUMA boxes divide it up, because what happens is you just have obviously a lot of contention. If you add this number and you scale this number up, this bus, just the memory controller, just won't be able to catch up. So on NUMA, what you do is you really have something called generally a cell. And the cell processor boxes, it's usually a one design part. So you have 4 CPUs plus memory in one local node. And you use, some people use buses, some people use, or not people, but companies use switches, crossbar architecture. So this CPU can access this memory, but it has to do a little loop around here. If you don't have software that is optimized to do this, or not optimized, but at least know what it's doing, obviously it thinks that all this memory is local to the box, which it is, but it doesn't know anything about latency on getting the memory back. AMD is something somewhere in the middle. AMD has an almost NUMA design in their normal dual-core quad-socket boards and processors. The AMD has something called the hypertransport. You've probably all heard it. Intel uses something called the frontside bus. The hypertransport really integrates the CPU and the memory on one chip. So it's super, super fast. It's amazingly, blazingly fast if you use an AMD chip to access your memory. The trouble is that if you have a 4 CPU board on AMD, all the CPUs are directly connected via an interconnected bus system, basically, to the other 4 sockets on your system. So in the worst case scenario, what happens is actually that if this CPU, where's my mouse there? If this CPU tries to access that memory up here, it needs to jump 1, jump 2 in order to get to that memory and then obviously retrieve the results back, which is almost an SMP problem. How many jumps do I need to do to get there? Which is actually a very good reason and the explanation right now that you don't really see AMD machines with more than 4 CPUs. I know there's a Sun machine actually that has 8 AMD CPUs in it, or 8 AMD sockets. We did some testing on it. You can buy it. I wouldn't recommend doing it for a high-end SQL Server load. It just doesn't do very, very well. Having said that, the 4 CPU machines of AMD obviously do a very, very good job on this. So the trouble is, if you go to more than 4 CPU sockets, you got to go to a different design, which is NUMA, which is where the world is going to right now. The interesting part about 4 sockets right now is that we've driven a huge performance over the past months and years. So if you look at what we do right now with the 4-socket, 4-core CPU, it is more than we ever did just about 5 years back on a fully fledged Sun E10000 Firebox. So the number of the things of throughput that we can drive right now, we can bring with a 4-socket machine, dual core even. We can really drive a SAN sometimes to its knees using just SQL Server. The trouble is perception doesn't go as fast as technology does. So the biggest problem we always have at Microsoft, and you all know this, is perception. If you hear Microsoft, if I would ask you and do just a quick brain game, I tell you Microsoft and you tell me what you think. Most of you would probably say SQL Server, otherwise you wouldn't be here. But if I do it to the general public and to the standard general CEO of a company, they will think Flight Simulator, Xbox, and if they have a really bad day, they think Windows ME. They're still in the camp of Sun, Starfire, or Oracle databases. So what have we done in terms of NUMA design that is actually changing in Windows 2008? It all started back in Windows 2000, then 2003. 2003 was the first operating system that actually allows us to tell us that we're running on a NUMA machine. Otherwise, we have no idea. SQL Server has no idea. It just sees 32 processes and says, I'm really happy. 2003 says, you're on a NUMA machine, and this is the layout of the NUMA machine. The trouble with this is that in the first implementations of SQL 2000 that we had, we didn't support it, even though we could see it. SQL Server Service Pack 1 and then Service Pack 2 actually fixed some of those issues. If you're still running on SQL 2000, Service Pack 2, and you're running on a NUMA machine, do me a favor and get off of it. There's a dramatic performance improvement in 2005. The real improvement will come with 2008 on Windows Server, not just SQL, because right now we face the problem on a NUMA machine that if node or if cell number 2 has an I/O request, all the I/O will probably happen at some other node. So you actually have a lot of memory messages going back and forth just to do a simple I/O. It is aware of it, but everything is right now handing on cell number 0. So if you start up Windows on 2003 and you're running on a NUMA machine, your entire OS, all the drivers, everything you have is actually running on the first cell, on the first node of your NUMA machine, which is why SQL Server by default installs on node number 1. So we don't have too much contention on number 0. However, you can easily see that if we can't spread at least the I/O out, we'll always have contention in the space. 2008 will actually alleviate a lot of these problems. This is an eye chart. The reason that I put all those little things on there is that you can download this presentation. If you ever happen upon a NUMA machine and you need to work on one, you can download the stack and you can actually see kind of what's going on there. So the first problem is not all hardware vendors with NUMA machines actually expose it the right way to us. If you're running on a NUMA, it could be that it's configured for Unix. Unix doesn't need the same health settings as we, therefore it doesn't work. This is what you should see on the SQL Server error log in there. This tells SQL Server this is what we have, a NUMA machine. So if we go general performance, what actually makes a big difference nowadays? In former days, we always had this processor cache, better performance. Doubling the number of cache in SQL really brought a good 5% gain. We saw that on benchmarks. One of the things we always did is more cache equals better performance. The trouble is that we're past this point nowadays. If you would double the cache on an AMD 2 megabyte cache box, it wouldn't get more performance. The reason is right now we are constrained by the bus. Doesn't matter how much cache we have on there. The other problem is caches are very different depending on the architecture of the CPU. An Intel CPU with 16 megabyte cache doesn't perform much better than an AMD CPU with 2 megabytes cache, if anything else would be equal. It's just a different architecture. Do not compare the different caches, and don't think that if I double the cache on this machine, you actually get a lot more performance out of it. The processor speed is another one. It can make a difference, but it doesn't always make a difference. We saw this when we got the AMD jump from, sorry, I'm not meaning to hack on AMD, could say Intel, but they're just a good partner of ours and we get a lot of their boxes. When we got the jump from 2.2 of 2.4, to be honest, didn't buy us that much. The reason was that the design that we have had other contention mechanisms. So if you go to an HP 585 generation 1 box and you update the processor in there, you might get 1 to 2% more performance, even though you have 0.2 gigahertz more frequency. The next one, the generation 2 585, is actually better, and you actually get a reasonable amount of performance. You have obviously a jump. If you step up a gigahertz, you will see performance improvement, but it's not the non plus ultra nowadays. You get everything you do will give you about 3 to 5% if we look at the CPU scaling. Also, frequencies are not comparable. A 1.6 gigahertz Itanium is not a heck of a lot slower than a Xeon running at 3 gigahertz. The memory. That's always a great thing. Right now we have this big run on DDR3 memory. It is a little faster. It has higher clock frequencies for the frontside bus. It does work, but you don't really get more than, if you really go to the very latest and most expensive RAM you can get, 3 to 5% at the max in an artificial benchmark setting. The reason that hardware vendors are really pushing it is completely different, and it has a little bit to do with scale up and scale out, which is heat. Heat in the data center is killing us right now. If you read the first page of this TechNet that everybody got in their wonderful bags on Monday, there's actually an editorial about temperatures and how much wattage we actually are using in the world just to cool down data centers. DDR3 runs cooler than DDR2, but it won't save your neck if you're having a 100% database workload. The funny thing there is you really got to look at the price. And not that I sound like a cheapskate right now. Usually buying the one below the top will give you more than enough performance, and buying the much more expensive system doesn't make a big difference. It's much better to buy more memory instead of faster memory. That is the one thing that obviously probably most of you know. What do we see nowadays in systems? 4 gigabytes per core is pretty standard. We have systems with over 256 gigabytes easily. If you look at the operating systems, Longhorn, I can still call it Longhorn, it's not yet released, so it will be Windows Server 2008. We support 2 terabytes of RAM. HP is actually working on a reference design to go up to 4 terabytes. I think that what you will see in the TPCC benchmark where it makes a difference. Otherwise, not really. The things that you need to look at when you scale up is what is your SQL buffer pool cache hit ratio? And it should always be at 99. If you're really bad at 98 or 97, don't go below that. If you have that, buy more memory, for God's sake. It seems to be very easy. You go to 99%, and that means 1 page out of 100 you will have to get from disk, which is very, very expensive in terms of times. If you go to 98%, well, you already increased your going to disk by 50%. It goes up quite dramatically, and you will see that those 15 milliseconds compared to a couple nanoseconds to access the memory will make a huge difference. The life expectancy, also, you want to have that very high, ideally over 300. The thing there is actually what happens with cache is related to what is on your database backend SAN. Most of us probably nowadays have SANs to store the database, and I'll go into this in just the next slides, but there's actually something very interesting happening there as well. We have the limitation 64 gigabytes on 4 gigabit DIMMs using the Intel 128 for AMD. Intel is just about to release actually 128 as well, so they are on the same level there. This subsystem really is something that makes a huge difference. We've heard it for the past, I think, 4 years now. The size of the disk is not relational to the speed of the disk. But to the rescue of all the disk manufacturers and the researchers that are trying to give us faster disks and drain our wallets by providing solid-state disk SSDs, is that we came up with something very ingenious. It's called data warehousing. Because the trouble with disks is not the sustained throughput. We cannot satisfy, or we can easily satisfy, the sustained throughput that SQL Server would ever need in an OLTP environment. What we cannot sustain is the access times for it. So OLTP designs, we need a whole bunch of disks. With an OLAP design, you need a whole bunch of disks too, but you're not that worried about it because you usually read 64K extents and not 8 kilobyte pages. So the sizing of the disk really is super important. If we look at, before we go into the demo, if we look at how many disks you need in any given system, to give you an example, internally at our systems, we are running with well over 120 spindles to run a, what is it now, 3 terabyte database. So it's not an enormously big database. It runs SAP, but you need a whole lot of distributing it. Now there's a little demo that I have prepared, which is really a hit and miss. Don't ding me on the evaluations, please, if this thing doesn't perform, because what I'm trying to show is very simple. I have 2 databases. Shouldn't take much time. 1 disk on one spindle on one physical spindle, and the other one has 3. I'm going to insert 600,000, 900,000 rows, and obviously the 1 spindle will be slower than the 3 spindles. That all was true until I hit virtual machine. Virtual machine apparently just does a single thread for all its I/O. So it's still somewhat serialized, but hopefully not too much. So let's see if we can see this. Perfect. So I'm having a machine here that is running three database instances. There is a standard instance, and I'll explain it now so I don't have to do it later, which is SQL, called just SQL. It's the default instance on the machine. SQL is running SQL 2005 standard. And then I have SQL Dev 01 and SQL Dev 02. If you all know Kimberly Tripp, I just used the same naming convention as her, but I didn't use her VPC. Those two, Dev 01 and Dev 02, are using the Enterprise Edition. I'll need the Enterprise Edition later on to show distributed partition views and to do some peer-to-peer replications on it. For now, I'm just going to go on the standard one. I have two databases, PAR1 and PAR3, and I'm going to run PAR1 obviously has one data file, PAR3 has three data files. And all I'm doing is I'm inserting a whole bunch of records from the all-too-well-known AdventureWorks system. It will usually take about 20 seconds for this. The part about disks is, especially when you go into SAN or EMC devices, we had some interesting parts there, especially when you go to EMC, really. The hardware vendors that sell you those SANs are all having different implementations, which is one of the reasons that you don't see a wizard for SQL Server setting any of this up, configuring your SAN. The only thing they have in common is a command called diskpart. But we had a very large oil and gas supplier, manufacturer in a way, in the United States that was running SAP on SQL. And we saw this one finished in 22 seconds. And I'll run the next one in just a minute. Provided I can go down here. And they upgraded, bought a new EMC. Had nothing to do with EMC, but that's what they had. And they started their load on it. They tested it, worked fine. They went into production, and all of a sudden, all hell broke loose. And they did call Steve Ballmer at that time. And they started yelling. And Steve Ballmer doesn't like to be yelled at particularly well. He likes to yell himself, but not vice versa. And so what happened was the performance was going, it tanked. It was completely crazy. So we looked at SQL, all the parameters were right, the data files were right. We just couldn't explain why it would not work. And so we called an EMC, and EMC guy said, this all looks really good. I don't see where the problem is. Well, the problem was obviously EMC presents meta and hypervolumes, and what we did is we presented to the operating system, not the spindles, we presented the hypervolumes. The hypervolumes were striped across the same disk segment. So they got the performance of floppy disk because they effectively did a RAID 5 on one spindle. Just nicely tiny slivers of I/O. So they really had I/Os they got about 5 I/Os per second or something. It was utterly bad. The morale of the story was that we need to look very, very carefully when we expose a SAN to the operating system, not necessarily SQL, that our spindles are done just the right way, that we actually really kind of understand what is on the same spindle, what is not on the same spindle. Because in this case, with that customer, obviously also the log files were just completely contention. So going to the demo back here, now I have to insert it into DB3. And this is going to be a very simple, very quick demo. Hopefully it'll do it in less than the 22 seconds I had just before. It usually goes in about 18. I'll tell you that right now. I did about 100 tests last night. That was the average. And this is the simplest of all demos. The other ones are going to be a little bit more interesting. But we finish in 18 seconds. I love predictability on virtual machines. Long story short, everybody got this. Shouldn't probably be in here if you wouldn't understand this. Parallelized to a big degree. So if we go, two more things on scale up, and then I'll go into scale out, I promise. Network, most commonly overlooked resource. Gigabit, standard. You get about 350 megabits on throughput if you use gigabit. The rest of there is InfiniBand, 10 GB. We saw some really good parts in there, but the network a lot of times was really one of the reasons why we couldn't scale up anymore, and we thought we needed to buy a parallel system. Reference design there is 1 NIC per NUMA node if you have a NUMA system. The file layout, I just talked about it. Make sure you parallelize. I'm not going to spend too much time on this. The general recommendation is 1 data file per CPU core. The reason for 1 data file per CPU core is that if you look at the memory allocation inside the data file, and you look at what the cores, all your CPUs are doing in your system. Whenever I need to allocate a page, any B tree we use, any page allocation, any page release, whatever we do on this data file, we go to this one IM page in SQL Server where we have 1 every 4 gigabytes or 1 every file. So if we only have one humongous file, even if we spread it out over a RAID array across many, many different spindles, we still have only one page every 4 gigabytes. So this is a very hot page, obviously, because we constantly allocate and deallocate space on there. And it's obviously in cache. Well, if we only have one page per core, this one page will be divided up to 23 or 8 cores, or how many you have. And so you have a lot of concurrency issues. This is why, in general, all reference designs we recommend one file per core, not per socket. The other part is space management. So the SQL Server has this great feature. One of the things we always advertise with is we are the easiest database to use. And then we are so easy because you double-click setup and you never have to do anything else. At least that's what our marketing folks tell me and you. Now there's this great thing about automatic growth of data files. My data file grows, it hits an end, my database doesn't stop. It used to do this in 6.5, it doesn't do that anymore. We have the auto grow feature, it automatically extends until the actual hard disk physical device is full, my partition is full. It works. We haven't really changed it too much ever since SQL Server 7.0. The interesting behavior on this, though, which you don't find on marketing.microsoft.com, is that the way it was implemented, the guy that implemented it, I'll bash my company a little. He kind of took the easy way out, and he had good reasons for it. But what he does is, let's say we have 6 files, each 100 gigabytes, and they're nicely growing, and they are just, we do the round robin proportional percentage fill. We insert our rows, and they might even have different sizes. So we reach the first file that is full, and the second file is not, the third file is not. So we continue inserting rows in 2 and 3. Shouldn't really go to that, but plus minus 1% is in there. And then all of a sudden, our database is completely full. All 6 files are full. Auto-grow kicks in. Guess what happens? File number 1 gets grown by whatever you specify, let's say 20 gigabytes, and the rest doesn't change. So I insert all my new rows into the first file. The other files are basically read-only and update-only by now. Once the 20% fill up, the second file gets raised by 20% or whatever you specify, and then the second file grows. So the entire thing of dynamic proportional fill goes out the window, and what you're having is a nicely serialized I/O. We kind of did a little bit of a change with the hidden trace flag in 2005. Jürgen has and I, a friend of mine who's responsible, he's not the developer of it. He's pushing very hard. We're pushing very hard to get to the developer to change it for 2008. So we'll see you will see probably within half a year if we did something. The change that we're requesting right now is that all files at the same time grow, so we continue our proportional fill in the end. But right now, set a pager off or do whatever you need. When you reach 2% free space on your database, manually extend your data files. We are actually doing it in our data center at Microsoft. We literally have pager, a guy on duty whose job it is to watch the database, and if the database fills up, he goes, logs in, extends the files, and that's it. So, just a quick example on a scale-up approach in a data warehouse environment, a large European supermarket chain with 360 billion rows, over 30 terabytes of data. They wanted to have real-time access on the data volumes that they stored in the database, and all users should have it, and it was over 600. And they actually went with a hardware manufacturer called Unisys that you all know, and I put them in there because they were nice enough to provide me the slide. On a cluster, a NUMA system, 8 cells, 32 dual-core Intels, 256 gigabytes of RAM, with an interesting over 1 billion records processed in less than 20 or a little over 21 minutes, which means over 1 million rows per second are going through SQL Server in parallel. This is, I think, a very, very good scale-up approach. You have still one database to manage. You don't have to manage. You have very little contentions when it comes to updates. Very little contention when it comes to inserts. It is the pure benefit of a scale-up solution. And you can still scale to over 1 million rows processed per second. If we go to scale out, there's several things that I'm going to mention. One of them is peer-to-peer replication. Peer-to-peer is something that was introduced in 2005, really. It's an enterprise server feature. You only have it in the enterprise edition. It is pretty simple. If you have a number of servers, all those servers will communicate with each other. You have no contentions in terms of updates. You can update any of those servers. It is the same database. You just replicate it throughout. There's different replication topologies. We could always do bus topology. This nice little thing here. What is new now with peer-to-peer replications is that we can do something called ring topology. The difference between those two is, if I go to SQL 2000 or the non-enterprise edition and I do this compared to this, this is pretty straightforward. If server A, B, and C are there, and let's say A did an update, A sends the update to B, B sends the update to C. Straightforward. In this topology, looks kind of the same, has the same effect, but if A gets the update from B, B thinks update is coming from A, which is correct. Now, B sends the update to C. C, however, then starts thinking, B sent me an update, so I'm going to send it to A. And we literally have a round-robin endless loop of replication in our database if we don't turn on peer-to-peer replication, specifically in SQL. Now, peer-to-peer replication is kind of tricky because it is one of those hidden features. Anybody here using peer-to-peer replication? None? All right. There's actually a wizard for it, and it's the first wizard that I know at Microsoft that we've actually hidden. Usually they're very open because we love wizards and we love mouse and we love all that. But there's no peer-to-peer replication. If you right-click, you don't see it. There's a little activation that is necessary for this. So I'm not going to go too much into the other ones. I'm running out of time. But it is bidirectional, and there's actually a little demo for this. So let me switch over. And here we are. So for the peer replication to work, I'm going to just replicate between two servers right now because, as I said, I need enterprise edition, and this little bugger out here is only standard, so I'm not going to use it. I did a quick project for this, so it's easier to show that later on. So the first thing I need to do is I'm going to replicate my PubS database. Everybody knows the PubS database. So I'm just going to replicate the authors table of PubS. So the first thing I need to do is click on replication and configure a distribution server. I have to do this with any replication. In this case, I'm just going to do it standard. Anybody who has ever done replication, this is a standard step. I'm not going to explain too much, but it will start the distribution server, set up a distribution server that actually takes those changes and sends them out over the wire to the other nodes. So I'm just going to do this. I do not want to start the server agent manually. I need to run the SQL Server agent for this. I've already configured it. I don't need to do a snapshot folder right now. There's a little warning that pops up. In this case, I can ignore it because the peer-to-peer replication, the replication I've set up, I have already done a database copy before the session and moved it to the other one, so they are somewhat in sync. Otherwise, I could share this one out. This is what it is complained about. It's not shared as a drive. So the other one can't get the original database copy from it, which is fine. I'm going to call it distribution. And I'm going to configure it by clicking finish. That'll take about 15 seconds. I need to do this on the other node as well. And then on both nodes, I have set up my distribution agents so they can actually start sending out logs. This, as you can see, nothing is hidden in here. So I'll do the same thing down here. Configure the distribution. I'm just going to run through it right now, so please bear with me. I will start it manually. I will keep it all the same. So now comes the tricky part. In the peer-to-peer replication, what I want to do is I want to configure it on one server and say, this is the one table that I want replicated to my other nodes, but I don't want to go to every node and singly set up this thing because it would be quite a bit of work. We always have we have something called a very well-defined network path in between. That means every node is connected to every other node. So if I have 4 nodes that I'm syncing with, I have actually factorial 4 of connections between those. It would be kind of a bummer if I would spend all day just setting this up. So in order to do this, I will have to start manually with 1, saying, oops, sorry. I create a new publication. And I said I will do the pubs database, the authors table. I will use transactional publication. You can see there's no peer-to-peer mentioned in here. It's just a standard transactional. I would like to publish authors. I can't use filters in peer-to-peer, just as an FYI. I can't filter the table to certain things. I just have to replicate everything. I don't need to create a snapshot, because I have already done that. Now, you see actually the wizard doesn't even let me press next here, because it says I need to set up a security context under which I'm running this. Now, if you've watched any of the security sessions, you know I shouldn't be doing this. I should give these privileges. For the sake of time, I'm just going to ignore those guys. Click on next. I'm going to create a publication right now. I need to name it something. I'm just going to call it pubs authors. Finish. It will create this. Now we have to remember in the next step that I have already created this because we get a very funky warning. And the warning usually doesn't mean anything good, but in this case, there's no other way of doing it. And you'll see in a second what I mean. Now, if I want to create, there's my publication. How do I start? There's no wizard that says do peer-to-peer replication. So what I have to do is actually go into properties, click on the subscription options, and set this little guy here to true. Once I change this little property of my publication, and I do right-click again, I have peer-to-peer topology. They were kind of hiding this to make sure that you know what you're doing when you're doing it, because it can cause quite a bit of traffic. So I can click on configure it. Next. It already figures out this is my original publication, so I want to do that. This is going to be an interesting point because all of a sudden it says SQL Dev 01, and if you look out here, I am actually on SQL Dev 01. I could set it up with my own database and pretend. We're not going to do this. We need to add a SQL server. So we are adding SQL Dev 02. And it already figured out I probably want to go to the pubs database. Once again, security is coming in the way. So once again, I'm going to ignore all the nice warnings saying, don't do what I'm doing. And this was for the agent, the log reader agent. I need to do the same thing for the distributor agent, the guy that then takes all those changes and distributes them to the other server, the same security settings. And you see it doesn't let me hit next until this is actually done. Click on next again. I already created the database manually on the other end. I don't need to do that again. And I click on finish. Now there's 4 steps. And what you see is it does create the publication and create a subscription. Now the interesting thing is this one we have already done. So you will see that there's a warning coming up saying, I can't do it because I've already done it. And if we hover over this, I think it'll actually show us what it wanted. The publication or its log reader agent already exists because we've done it in order to enable that little flag to be changed to true. So whenever you set this up, just ignore it. Now if we click on close, and we open up our local subscriptions, you will see that on both databases. What am I doing? Under replication, we have these configured. So what I'm going to do now is just going to run a quick select pubs from authors on SQL Dev 01, so on the original server up here. It gives me all the authors table. And my update, I'm going to just name everybody Kevin, good friend of mine, and change everybody who lives in California to the name Kevin, because Kevin is, in fact, somewhat of a Californian name, I think. So we just do it on SQL Dev 01, however, not on Dev 02. And just to make sure that you see that this is all right, just run this. 15 rows have changed. And if I now go and select from Dev 02, you will see that there's a whole bunch of Kevins in there, because the replication is very, very fast. We have a latency usually of 2 seconds for it to replicate. You can set that to, well, actually 4 seconds, I think. You can set this reasonably to 2. I didn't do it in this one. You can even set it to 1. That 1, 2, and 4, what I'm talking about is settings. There's an option for it to set. I'll show it in the next slides. Don't set it to 1. Weird things start to happen when you start distributing every second your updates on the network. Not a good thing. 2 is actually very, very good, depending on the size of data you're transmitting. So that's peer-to-peer, a hidden feature since 2005. It works really, really well. We actually have quite a few customers that are using it because it allows you to really have a distributed database that you can update on any node. You have a relatively low latency, and it does a very good job on keeping you on keeping the actual round trip very, very good, depending on your package size. Now let me just close this guy and open the next one. So what we're doing with peer-to-peer replication for the most part is actually set up a well-connected system that I mentioned earlier on, which is everybody's connected to everyone, rather than the just enough scenario where you just have a single link, and if a link breaks or 2, then you're kind of out of luck. This is the customer we have. It's an online gaming corporation. When I show the slide in the US, it's kind of funny because you have to put this big banner on that says literally across the entire thing saying online gaming is illegal in the United States and you get arrested if you run a company like that. Those of you that follow the Financial Times, whenever one of those executives of multi-million-dollar corporations happens to jump on MaxJet or something and goes to New York, they usually just arrest him at the airport. It's pretty interesting because it's relatively legal in the UK. But anyways, online gaming corporation needed a replication scenario. They have 2 different databases, and they have a whole bunch of affiliates and local servers that actually serve the gaming. And you do the gaming, there's the gaming database, about 7 days of games in there still, archived because you don't want to have too big of an OLTP design for performance reasons. They push it over to the distributor. They actually match it into single databases. So every little affiliate has their own little database that then gets pushed to the internet. If we look at the performance on this, it's actually very, very good. We have a total low latency from 20 seconds, less than 20 seconds. So the very end guy in a very different network will get it within 20 seconds if a change happens. But the nice thing is, you actually can go back even 7 days, the architecture they have done it, and we can actually push, depending on if they have a disaster on the affiliate side, on the very end node, you can push the entire replication, the entire database, at a very reasonable amount of time. For the last 7 days, you can get your entire history back. So it's a very good process for them. The lower polling interval is the little setting that you can set to 2 if you want a very low latency in terms of polling it. Another new thing that officially was kind of hiddenly announced in 2005 is the scalable shared database. Scalable shared database means that you can have, we officially support up to 8. There is not really a limit of 8 in our product, in the enterprise version. You can support up to 8 systems against a single database. You have different CPUs, different boxes connecting to the same SAN. The problem is it's read-only. So it's a limited scenario set. And the reason it was kind of hiddenly announced was that the books for SQL 2005 were pretty much done when we introduced that feature. So it was never officially probably properly put in when we released 2005 by now. A lot of them have been updated, so it's in there. But it's great for reporting services. It's a scale-out solution when you have stale data. One of the things you got to think about scale-out solutions is what kind of data do I actually have in the databases that I can partition up? In this case, the data would be catalogs, something that rarely changes. There's a customer that uses the company phone book, which is a humongous company. They need to publish it to 23 different applications. The applications don't want to go to this one central location he has, so he needs to copy it. And they actually use a scalable shared database, and they do a rolling upgrade. So what they have done is they have 2 of those scalable shared databases because they need to be updated every Sunday. And the clients connect to one with a failover scenario to go to the other one. So if he updates one, he takes them offline. Clients go to the old copy. When the update is done, the clients connect to the new copy, and then he updates the second part. It is the closest we have to what Oracle calls RAC. As I said, we don't have something called Oracle RAC. We won't release one in 2008 either, for the simple fact that there's other problems that I personally have seen, and that you look at our architects, why they have done it. It's very interesting to go to, but I'll do this. I'm happy to do this in a one-on-one. I won't do it on stage, obviously. You need a SAN to do this. This is why I can't demonstrate it. I didn't bring my little SAN over here and start messing it up to show a scalable shared database. But another part of scaling out, another option you have is distributed partition views. Hands up, who's using distributed partition views in here? Well, that's first, nobody. Okay, so scalable distributed partition views are the idea that you have several databases, and those databases share a table. So you have a table that is partitioned by a key. In this case, the key, let's say, is a number that goes between 1,000, between 1 and 4,000 and anything greater. So if I have a record that I want to insert that is 1532 in value in the key, it would actually go to my connecting server, because I'm only connected to one server. And that server would say, I know about this table and I have part of this table, but it actually needs to be stored on that server over there, and that one will actually then store it in its data file. So it is a very good way of really distributing your data. We do a lot of things in parallel. We already had this in 2000 to a part. We perfected it a little bit more in 2005. Guess what? We even perfected more in 2008. And what I say with perfecting is, it's not really a bug, but the behavior that you would assume this thing will do is not what it actually does. And I'll show you in the next 5 minutes what this will be. So the tables are partitioned across multiple databases. You can have more than one table partitioned across multiple databases. The SQL engine on each node understands the partitioning scheme, and it understands that there's a data key that is set. And usually you can even have rolling windows. So you can say my years, and you can divide data up by a year. So every year you have a different table on a different server for that, or the same table on a different server. The demo for this is pretty straightforward. What I'm going to do is I'm having a database called TestDB, and I'm going to use all 3 servers for it. So SQL Devo 1, the enterprise server, SQL Server Devo 2, the other enterprise edition, and the standard one. And within TestDB, I'm just going to distribute up a table. It's called orders, and I'm going to fill this with Northwind database data. So right now, if we look at the tables, oh, that's the pubs table. What am I doing? No tables in there. Nothing in there. So the third one won't have anything either. I have 4 scripts. The first part, the 3 first ones, I'm going to go through relatively quickly. What this script does is we connect to the first node in this, which is SQL Devo 1. And we're going to name the nodes. That means we need to make SQL Server aware that there are other servers out there that are going to be linked to this server. It's a pretty straightforward process. I could use a wizard, but this is just a heck of a lot faster. I'm also going to set the SP Server option lazy schema validation. Lazy schema validation means that SQL Server will not check that the schemas actually match up of that table on each node until it is right before and doing some changes to it. Makes it a little faster for our setup right now. So I'm going to run this one. Nothing exciting is happening. It just says I'm done. I have to do the same thing for the second node. Now, if you look at the parts, the second node says add linked server, server node 1, which is dev01, node 3, which is the default instance SQL. Sorry if I didn't do this on the first one. It does kind of the same thing there. But the difference is this one defines node 2 and node 3. Dev02 is node 2, Dev03 is node 3, or SQL is node 3. So I'm going to turn on the command here, run it. It just comes back to me. I'm going to do the same thing for the third server. So what this means is all my 3 servers are now knowing about the other 2. So every server gets 2 entries in their linked server list saying there's server number 2 called that and server number 3 called that. This one, however, node SQL, remember, is the standard SQL server. It's not the enterprise edition of SQL. So if I run it, I get 2 warnings. And the warnings say lazy schema validation is not supported. So a standard SQL can participate in a distributed partition view, but kind of not really. There are a lot of limitations on it. For the demo on stage, it's fine. If you want to show it to your boss, it's fine. When you implement it, I think you should talk to the next Microsoft sales rep and upgrade your version to Enterprise Edition. So having said that, all this is done. So what we have done is we've set up all these parts. And if I just close my views here, you can actually see it. Every SQL server, starting at Service Pack 2, you can actually see this very well. If we go to, where are we here? Server objects, under linked servers, you will see that there's my node 2 and node 3. And I can actually now, in Service Pack 2, there's a test button. So I can check it if the test connection actually succeeds. If you're not on Service Pack 2, that test is no there, although it will still work. So going to the, going to this, have I executed this? Yes. The first thing I'm going to do is I'm going to use my testd, and I'm going to create a table called orders A on the first node. So I'm going to go to SQL dev01, and I'm going to create that with the constraint that the order ID, everything that gets inserted into this table should have an order ID of less than 10,500. The order ID is going to be my key on where on those 3 servers I'm going to insert and store the records. Everything less than 10,500 goes to dev01. So I'm going to just execute this. Going down a little to SQL dev02. I do the same thing for the second server. I'm going to create table orders B. And the constraint there is everything between 10,500 and 10,750 goes into the node number 2. Now going into the third node, just called SQL as the default instance. And everything greater than 10,750 will go in there. So we now have on our databases, if I refresh this, orders A. If I go down here, you will see orders B. And down here, up here is orders C under my SQL. C, everything over 10,750, B, everything between 500 and 750. Got to remember this because there's going to be an interesting test coming up. So the first thing I have to do, since I just created the table, I need to put some data in there. So I'm going to do this right now. And I'm going to do a union all. First, I create a view, and then I'm going to insert into the table. I'll do this in one step into the table itself. The view is a union all between all those nodes. So I'm going to execute against the view, which will grab the data from all 3 databases into it. It will insert about 800 something records. There we go. Now, if I select anything from dev01, which has everything between 10,500 and 10,600, or less than 10,500, I will get the results back. That's pretty straightforward. The interesting thing is now if I look at the query plan. So if I look at the query plan, Oh, that was actually the wrong query. I'll do this. I just do a select star with all from all the rows, not just the ones. You can see that there's a distributed query happening. And because of caching right now, I have a lot of remote query going on here. But if we look at this query plan, we will see that it does clustered index scan on this node, and it does remote queries on the others, and then it concatenates them and gives me the results set in here. Straightforward, we send the query to one, all three databases respond because I want all the rows. If I do a where clause, as I did before, it will show me that there's only remote query. I don't have to go to the local node because I'm just querying the order ID between 600 and 700, which we know was on dev02. That sounds pretty darn parallel to me. Great. The problem with that is if I do something like this, where it spans more than one, oops, that wouldn't work, would it? I need to connect to this, there you go. If I do something like this, where I actually go out to 3 parts, what SQL Server does is, it does all this in parallel, that is correct. So those happen, since they are on physically different machines, at the same time. The trouble is, this happens serially, and guess what? It waits. So if this guy is really, really fast, and this guy is really, really slow, nothing's going to come until everything has been arrived over here. So the actual data delivery to the client still happens in a serial manner. The actual retrieving happens parallel. There's another caveat. Let's say we do this nice little thing. We do a remote query. It goes off to SQL dev02. I'm going to shut down this guy, SQL. SQL is node 3. It has every record from 10,750 and higher. I'm going to stop this guy. So SQL with the records 10,750 and higher is down. But this query, I don't want anything 10,750. I just want whatever is already still available. If I go to this, boom, doesn't work. So it's not really a high availability concept. And I'm going to end this demo right here because there's not really a way out of it except to start with high availability for another hour. Distributed partition views is great for parallelizing certain types of data that are huge, that are key indices, for sorting it. But if one node fails, even if the data that you want isn't even on that node, if you lose connectivity to that node, whatever it is, your entire query will not work because the main server will always test all the nodes if they are available, and then we'll start dividing up the load depending on where it needs to get the data from. One is down, doesn't work. So be careful with this. Having said that, a lot of customers are using it pretty successfully. So the cautions when you scale out. What are we going to do when we scale out? The biggest thing we have to watch out for is update frequency. If you have a heck of a lot of updates in certain hotspot areas that you can't divide up depending on your data type, I just have to say scale up. Scaling up nowadays is a lot easier than it used to be. It's a lot cheaper than it ever used to be. And there really isn't a reason that you want to use standard servers with 2 CPUs and have a whole bunch of them in your data center and have them all work in a virtual grid. Some people say high availability, some people say scalability, but I can show you differences why it's not as easy as it seems. We all cook with water. It's no magic. You have delayed inserts, you have failover times that are not super good, or at least they're not any better than the mirroring in SQL would provide. So these are all the things, but it introduces complexity to a certain degree. So this is all the things that we are fighting with right now and coming up with what makes sense to scale up or scale out. Update frequency is a big one. If you have a read-only database, it's very easy to scale out. If you have a lot of updates, it's not. Code flexibility is another thing. How flexible is your code? If you want to go with distributed partition views, or if you want to go with a truly distributed database, can you make changes like this? It happens sometimes when you go into a SOA project that you say, I'm going to re-architect my data providers. there's a good chance that you can create your code more flexible. A lot of times if you go to already written applications, out-of-the-box applications, it becomes kind of tough. Data partitionable, how much can I partition my data? It's actually surprising to me. I've seen quite a few customers that had data that wasn't really relational, and it wasn't made relational very, very well. It was very weird data. It was data that didn't make sense to be in the same database, but they still stored it in the same table. And so there's a lot of times parts where we can take the data out and actually put it in a completely different database even. It works. It's very easy to do in a lot of parts. And last but not least, data interdependence. Are there any islands of data that you have? And if we look at really what we do with our databases right now, where do we have a need to scale up or scale out? Either one can be done in either way. There's no bullet point where you say, if you have this application, you have to scale up. If you have that application, you scale out. Unfortunately, it's no longer true because the hardware vendors made their machines too damn fast right now. The two main reasons, as I said, for scaling out with any product on the market is usually twofold. Some say I want high availability, some say I want scalability, some people say I want both. And that's the whole point. I want to be highly available and highly scalable. And you can do this by using a mixture with SQL Server on any platform. And it's not very hard to administer, and it's not very hard to set up. And it's certainly not very hard to scale up if you do all the right things. And it has a lot less complexity. So the trouble we have is there's a lot of hype in the market that I see right now. And unfortunately, this dream of like, I'm just going to add another box to my grid and it's just going to works if you have very independent workloads. Outside the database spectrum, you can see that at City at Home, for example, where you have nicely partitioned data parts that can be processed individually, completely independent of what else is happening. In most OLTP scenarios, we don't have that. They are already in different databases. So how do we divide something up that actually belongs together is kind of a tricky part. So the summary, if we look at scalable shared databases, peer-to-peer replication, linked servers, DPVs or data-dependent routing, it's really coming down to, for most OLTP designs, update frequencies. And my personal favorite on there is peer-to-peer replication or distributed partition views if you need to do it. There's very little conflicts on peer-to-peer replications in general. You have a lot of updates that you can push through, provided you have a good link between the nodes. Distributed partition views is very good if you have data that actually moves. Archives per year come to mind. Anything where you have a rolling window works really well. And if you have read-only, of course we don't have that discussion, scalable shared databases. It's very simple to set up, works very reliable, it's very, very, very fast, and you can do a lot of nodes on there. With that, I think I have 1 minute to have any questions. If you have any, feel free to ask. Happy to give you guys my contact info if you want to come up later on. Sir? There's your answer, maybe. No. I'm sorry, could you repeat that question? Yeah. So you said when you mirror with and the RAM requirements for mirroring, or how mirroring would affect the performance of the database depending on the RAM. It actually does impact it to a good deal, but because it's a direct connection and it's not using a peer-to-peer replication, anything of those scenarios, we have seen scalable, super big databases, I would say in the many terabyte ranges with updates of more than thousands or 2,000s per second that are successfully mirrored. Depends on what mirror technology you use. So a lot of times they use asynchronous mirror. So it doesn't, when you write and it goes to the other mirror, it doesn't wait for the acknowledge of the other log to say, dear client, I'm done. If you need 100% availability and you look at your mirroring scenarios and you say, I need to make sure that they're both in sync and they can kind of go in a lockstep. I do the update here, I write the log over here on the second mirror, and then I'm going to tell the client I'm done. It gets a little bit more tricky, but if you're in the same room and it's not spanning cluster. Well, we've seen you can push depending obviously on the transaction. On an OLTP workload, and you have rows that are not longer than a page, you get a couple thousand updates in per second. So it should not be a big problem on you. To make a long story short, the answer is you shouldn't have a huge performance impact for this, provided you're running on more than one CPU box. Did that answer it? Kind of. Oh, the solid state disks. Well, solid state disks are very interesting. Solid state disks are super fast, right? And for my notebook, I would love one because I like to. It's one of those machines that looks great, and it's a company that does beautiful perception art, but I just really want to kick it every other day. I can't do this because it has a moving head. So solid state disk access time is, I have a solid state disk. It accesses in about 0.1 millisecond. Compare that to your usual drive, which accesses, if you're really good, 10 to 12 milliseconds. 0.1 versus 12, you're 120 times faster. Trouble is with SSD, the throughput. You get about, and the consumer grade, you get about 17, if you're really good, 17, 20 megabit second. On the enterprise ones, you get more, but the throughput on the solid state disks is not as good as it is currently on the spindles, especially when you go to the outer part of the spindle. You have about 40 to 50 on the spindles. So it depends on your workload. If you have a heavy OLTP scenario, you say, I'm just having a lot of tiny little records that I need to update. Solid state is it, if you can afford it. If you have an OLAP environment where you have huge rows of data, and you really need to calculate across vast arrays, and I/O is bound by the volume, not by the access time, I would go with spindles. Get a whole massive set of disks, make sure you have the right extent on the disk, and do that. Solid state is not quite there. It's not the throughput for massive data volumes. It's great for, give me that record really, really quickly. Anything else? All right. Thank you for staying. I think we got one or two more, and then you can explore beautiful Barcelona again. Thank you.